Hello, everyone. My name is Stephanie Myers. I'm a PhD graduate student, and my presentation is called Effects of Beta-phenyltryptamine on Lipopolysaccharide-Induced Chemokine Expression and Sickness Behavior in Mice. Now, it is important to point out that neurological conditions such as central nervous system infection, neurodegenerative diseases, and psychiatric disorders all have neuroinflammation in common. And there are several antidepressants and antipsychotics currently being used on the market that reportedly possess limited anti inflammatory properties. However, most of the pharmacological agents used to treat these disorders are not considered to be potently anti inflammatory. What we have discovered so far is that the anti inflammatory drug that can access the central nervous system and is well tolerated is a selective mu opioid receptor antagonist called beta-phenyltryptamine, beta-FNA. And our previous studies found that when co-administered, beta-FNA inhibits bacterial lipopolysaccharide LPS-induced sickness behavior and neuroinflammation in mice. In the present study, we examined the extent to which beta-FNA is protective when treatment occurs several hours after LPS administration. Beta-FNA's protective effects on an earlier time point of 8 hours post-LPS, and the effects of naltrexone in our in vivo model. Naltrexone is a non-selective opioid receptor antagonist from which beta-FNA is derived, and previous in vitro findings indicated that naltrexone does not inhibit inflammatory signaling in astrocytes. Our study used MILC57 mice, and they were administered an LPS dose of 0.83 milligrams per kilograms via IP. This dose is a well-established dose that causes neuroinflammation and sickness-like behavior. This was then followed by treatment with beta-FNA at a dose of 50 milligrams per kilograms IP. And this dose is based off our effective dose from our previous 2017 publication. Or, depending on the study, the mice was given an equimolar dose of naltrexone at 38 milligrams per kilograms IP. This was then followed by a 10-minute open field test and termination at 24, 8, or 6 hours, depending on the study. Levels of inflammatory chemokine CXCL10 and CCL2 levels in the tissue were measured by ELISAs. I would now like to bring your attention to Figure 1. This experiment was designed to determine whether beta-FNA was protective when treatment occurred hours after LPS administration. Our previous study looked at beta-FNA and LPS as they were co-administered. Now, notice that in this particular pilot study, a saline-only group was not included because we already knew from our previous work that saline does not impact these factors. Key things to point out here are that our LPS group showed a reduced distance moved and duration in the center, and there was also an elevated level of CCL2 and CXCL10. Beta-FNA treatment at 4 and 10 hours after LPS administration seemed to inhibit CCL2 levels in the brain at 24 hours, more so than in plasma, yet it did not reach level of significance. The study shown by Figure 2 was designed to compare the effects of beta-FNA treatment immediately after LPS administration versus 4 hours post-LPS, and assess the effect at an earlier time point of 8 hours, which is when sickness behavior is most pronounced. And what we see is that the mice in the LPS only group displayed a reduced distance moved and duration in the center, this indicating sickness behavior. Beta-FNA treatment simultaneously or at 4 hours after LPS was not protective, and LPS induced a more pronounced expression of CCL2 and CXCL10 in both the brain and the plasma. However, beta-FNA did not significantly affect expressions under these conditions at 8 hours. The experiment shown by Figure 3 was conducted to determine the protective effects of naltrexone treatment immediately after LPS administration. So what we see is that LPS significantly decreases distance moved and duration in the center when compared to the mice that received saline only. And the mice that received both LPS and naltrexone showed no significant increase in either the distance moved or duration in the center. As for CXCL10 and CCL2, there was an increase in inflammation when comparing the LPS group to the saline group. However, there was no significant decrease in inflammation in the groups that received LPS and naltrexone. To conclude, together with our previous findings that beta-FNA is protective when administered immediately prior to LPS, it suggests that the timing of beta-FNA treatment is critical for neuroprotection. Also, naltrexone was not protective in this in vivo model. However, further examination of the anti-inflammatory and neuroprotective effects of beta-FNA are necessary. Moving forward, we would like to further assess the temporal effects of beta-FNA on neuroimmune signaling, determine the extent to which beta-FNA differentially affects LPS-induced neuroimmune signaling across brain regions, examine the extent of beta-FNA on LPS-induced inflammatory signaling in peripheral tissue, and we would like to assess the effects of naltrexone after 24 hours. And with that being said, thank you for listening. That concludes my presentation.